Now that we've built up a little bit of intuition, we're going to look at the behavior of limits and some properties of limits. So there's quite a few basic limit properties in this section of the book, and we're going to look at some of those properties here. Let's assume I have a function whose limit as x goes to some value c is L. And I have a constant number which we'll call b. Well, if you take the limit of a constant number, no matter what x goes to, that limit is just going to be the constant number. One way to see this is by thinking of this constant number as a function itself. Let's think about a function g of x equals 5. If I take the limit of g of x as x goes to any number, well, what is the output? The output is always 5. We can think about that algebraically. If you create a table, no matter what you're plugging in for x, you're getting 5 as the y values. You can also think about that graphically. So graphically, g of x equals 5 is just a horizontal line. So let's say we want to approach the number -2 in my x value. So x is approaching -2. Well, as we approach -2, we're going towards the y value of 5. We just basically stick on the y value of 5 the whole time. So limit of a constant number is just going to be that constant number. Another thing that we have is that whenever you take the limit of just x by itself, so think about this as the function h of x equals x, as x approaches any number, you get that number back, okay? This y equals x is just the slope, is just a line with slope 1. And therefore, you get essentially the identity function back, f of x equals x. Each time you get closer to a certain number, the limit is approaching that number. So graphically, what we have here is a line with slope 1. And so as x approaches 4, we're approaching the point 4, 4. Again, think of it as the line y equals x, or f of x equals x, or however you want to do that. So as your function, as your x value gets closer to 5, the function value gets closer to 5. So we can see here that limit as x goes to c of x would be c. Now, another thing that we can do with limits is we can take a coefficient of b, we can multiply it times a whole function, f of x, the output of a function. If we take the limit of that as x approaches c, what we're going to get is the coefficient b multiplied times the limit of f of x. So in other words, if I multiply my function by a constant, I can multiply either inside the limit, or I could have multiplied outside the limit. So we see here limit of f of x as x approaches c is L. So if I multiply both sides by b, I can take that b and move it onto the inside there. Other features of limits. Well, one feature involves what we dealt with in terms of our intuition. If I have two functions and I take the limit of those functions as x goes to the same value, so x has to be traveling to c on both of these limits. If they both exist, and for instance, limit of f of x as x approaches c becomes L, and limit of g of x as x approaches c is k, then you can take the limit of the sum of the two functions and just add up the L plus k. You can also take the limit of the difference, so you could have subtracted and gotten L minus k. That's what this first one is saying. It's saying you can either add or subtract the two functions, and you would add or subtract the limits. Now, it is important that all of these limits are going to the same x value. So they're all going to c here. Well, sum and difference of functions work out. It turns out the product of two functions also works out. As long as these limits exist, then the limit as x goes to c of the product of f and g is equal to the product of the limits. And moreover, if I do this same thing with the quotient, if I take f of x divided by g of x, and then take the limit as x goes to c, what we would get is the quotient of the limits. Now, this quotient, we do have to worry about when k is 0. When k is 0, since we don't want to divide by 0, we don't want to have that. But in any other instance, if k is not 0, then we can find the quotient, the limit of the quotient, by taking the quotient of the two limits. Other things that we can do, well, we actually can take exponents of limits of, so if I take the limit of a function raised to the nth power, then I can get the limit to the nth power. And if I take the limit of a function to the nth root, then I can just do the nth root of the limit. Now, once again, we have to be a little bit careful that we don't get negatives in here when n is even, because that won't turn out to be a real number. So that's kind of what this is saying. If n is even, then my function values have to be positive around this c, so that I can actually take the proper root. Now, one other property that we will look at is the composition of functions. It turns out if I take a limit as x goes to c, and I take the limit of f of x as x goes to c, I get out an L. And if the limit as x goes to L of g of x is k, and g of L is also k, then I can compose these things. Now think about what's happening here. Limit as x goes to c, That's basically turning this f of x into an L, and then I'm taking g of L and then getting a k. So it's a two-step process. The inside function gives you the limit L, and then you take g of L and you end up with a k. So those are some basic limit properties that we're going to be utilizing when we solve limits analytically. Now, let me give you an example of how this is going to work. We're going to take the limit as x gets closer to 4 of 5x squared plus 2x minus 9. Now, this is a polynomial. And so what we're going to do is we're going to use the basic properties of limits that we just figured out. One of them, the fact that exponents can be done this way. Another one, the fact that we can add and subtract pieces individually. Another one that says limit of a constant is the constant. And the last one that says limit as x approaches c of x is c. Okay, so we're looking for the limit of this polynomial as x goes to 4. Now, what we're going to do is we're going to say, well, because each of these terms is a separate piece, and I know limit of the sum of things is equal to the limit of each part, I can take this limit and break it down into 3 different limits. Limit of the first term plus limit of the second term plus limit of the last term. And it doesn't matter on that last term if you put the negative sign out in front or the negative sign inside, because remember, it works exactly the same with sums as it does with differences. So once we have this, then we can say a few things. Well, one of the things we can do is say that since we have a coefficient in front of our x squared, one of the limit rules that we did said that if I have a coefficient, a b times f of x, then that's the same thing as if I said b times the limit. So what I could do is I could pull that 5 out front. And in the middle term, I could pull the 2 out front. Okay. I'll come back to this limit of 9. Don't worry about the coefficient there. Well, now that I have this, I can say these last two are limits that I already am going to know. But what about this x squared? I want you to think of that as the entire limit squared. Again, what I'm utilizing is my rule that says if you take an exponent of the function inside, I had a function inside which had exponent of 2, then that's like taking the limit of the function all being squared. Now at this stage, this is a fairly obvious thing that I'm going to do. I'm going to say, well, in those very first properties, we said limit of x as x gets closer to a number is just that number itself. Limit of x as x gets closer to the number is just that number itself. In this case, that number is 4. And then limit of x as x gets closer to a number of a constant is just the constant. So we get 5 times 4 squared plus 2 times 4 minus 9. When I calculate that out, I got a 79. So there we go. That's how we could use those basic properties to find this limit. Notice that this was a fairly easy process to do. And once you get good at it, you can say, oh yeah, this is a polynomial. This coefficient, you can do a lot of this in your head. This coefficient pulls out front. I'm taking the limit of x squared. This coefficient pulls out front, taking the limit of x, minus limit of 9. That's just a constant. Limit of x squared is just like limit of x quantity squared. And then that means limit of x as x goes to 4 is 4. Limit of x as x goes to 4 is 4. So once you get good at this, this will become a fairly straightforward process. So there you go. Limit of x goes to 4 becomes 79. So what I'd like you to do is do this problem here, 3x plus 4 over 5x squared, taking the limit of that as x gets closer to -2. And I'll explain that in the next video. But make sure you do it on your own. And on the next video, I'll explain it and give you the answer.